How can we prove that root 45 is irrational? Well, we can try the familiar way, the way you're expecting. 45 is 3 squared times 5, and root 45 is 3 times root 5. And so, we prove that root 5 is irrational, and this is very similar to proving that root 2 is irrational. I will leave a link in the description box to a video that shows you the classic proof. It's easily adapted to root 5, but we need one more thing. We need this. If r is rational and x is not rational, then r times x is not rational. Okay, so if we have a and b, then this is proved, no problem. Okay, for this, I would like you to do it as an exercise. So it's pretty easy to do. Just try that. Well, so this is what you're expecting. This is probably the best way to do it, but this is not how we're going to do it in this video. In this video, we're going to do it the hard way. And now, why should we do things the hard way? Well, in addition to it being an exercise in patience, doing things in an unusual or an unfamiliar way can give you some enlightenment about the problem. You can gain some insight. And I think that might happen here. I think that I gained some insight into the classic proof by doing this hard way example, and maybe you will too. So we're going to proceed basically along the same lines. Root 45 is m over n, where the GCD of m and n is 1, so they're coprime. And so 45 is m squared over n squared, or m squared is equal to 45 n squared. Okay, so that's the first thing we should highlight. So let's think about this. Well, since 3 divides this, 3 must divide this, yes? So 3 divides m squared. But according to those little lemmas that I proved in the video in the description box link, 3 must divide m as well. But here's where it takes a bit of a left turn from the classical proof. 3 divides m, and since the two are coprime, it must be that 3 does not divide n. Because if 3 divides n, then both m and n have a divisor of 3, so this wouldn't be true here. So that's quite interesting. So we have these two facts that we can now use. So since 3 divides m, we can write m as 3a, for example, and we can put it into this expression, and we get 3a squared is 45n squared, and that is 9a squared is 45n squared. So let's divide some stuff, and we get a squared is 5n squared. Okay, so that's worth highlighting like this. Now comes a very interesting observation. Watch this. Since 3 does not divide n, then 3 does not divide n squared, right? Okay, so we know that, all right? We know that from here. 3 doesn't divide n, 3 doesn't divide n squared. So 3 does not divide n, 3 does not divide n squared, but also 3 does not divide 5. So these facts combined means 3 does not divide a squared, because look what we have here, a squared on this side. Okay, so this implies, by the mini little lemma, that 3 does not divide a either. So let me write down the important things that we have discovered. 3 does not divide a, and 3 does not divide n. And we have this expression here, a squared equals 5n squared, this equality, that must be true. All right, so these are the facts that we will use to prove that root 45 is not rational. So how do we approach this? Well, we take a, there are some possibilities for A. Let's write this neatly. 3k plus 1, that's not divisible by 3. Or A is 3k plus 2. So that's two possibilities. Other possibilities, yeah, amount to the same thing. And now for n, I have something similar. Let's say n is 3h plus 1, or n is 3h plus 2. So now I've got these possibilities. I have 4 possibilities to check. And this is where the hard part comes into play. It's just a lot of algebra, and I'm going to shorten it for you and show you how it works. So let's start with case 1. So case 1 is this and this. And we'll plug it into this equation here and see what happens. So we have case 1. So A is 3k plus 1, and that's squared, and that's 5 3h plus 1 squared. Okay, so I get this. Now I'm going to put all the things with variables h and k on the left and put the numbers on the right. Now factor out whatever I can, 3 and... So let's examine this carefully. This is an integer. So what we have here is integer equals 4/3. And that's impossible. So this is a contradiction. Now we have to examine the other cases though. So the first case results in a contradiction. So let's try the second case. The second case will take this and this. All right, and I'll plug this in and now expand everything. I get that. And now I'll rearrange all of the k's and h's on the left and the numbers on the right. I get this. Now I can factor out a 3. And I fixed some silly algebra mistakes that I made here. Okay, so now it's okay. I get 19. And this is an integer. And integer equals 19 over 3, which is impossible. Very interesting. Okay, great. So that case is impossible. Actually, I'm going to continue here because I want to keep my stuff up here. So I'm going to erase some of this. Case 3, what should we look at? Let's take this one and this one. Okay, so that's 3k plus 2 for A squared is 5. And I have to make sure I don't make the same algebra mistake. It's easy to just forget this one. Okay, 3h plus 1 squared. All right. I expand. I do the same thing. I bring the numbers to the right. Let's see, is that right? 5 times 1 is 4. 5 times 1 is 5. Minus 4. Okay, take this 4, bring it to the other side, like over here. I get minus 4. Okay, so I factor out a 3. I can do that here. Look, 3. So I have this, and this again is an integer. This is here is an integer, and the whole thing should be equal to 1/3, which is impossible. So you see, this is an exercise in patience also. Just have to be patient. If I make a mistake in algebra, erase it and fix it and continue. The last case, let's take these two here. I get this. Let's expand everything. Great. Now, same procedure. Bring the numbers to the right and fix this little mistake here, 12h. Okay, that looks good. So again, 3. Every one of these is divisible by 3, so this is an integer. And this is equal to 16. So we have an integer equals 16 over 3, and that's impossible. So we did it. Okay, every case is impossible. All the 4 possibilities are impossible. And so therefore, square root 45 is not in Q. And that's very interesting. What can we say further about this? Well, here are some points to consider. Can you make this proof work for square root 2? Well, that's very interesting. Can you adapt it to the classical proof? That can give you some insight onto the question of how similar this proof is to the classical proof. You can try this proof on other numbers. Maybe it works for entire classes of numbers. Why don't you experiment with that? Find out. Let me know what you find. Another thing you can try is to introduce modular arithmetic. That will make a lot of this more elegant. Finally, if you find something interesting, then let me know in the comments. As always, like, comment, and subscribe. If this hard way proof gave you some kind of enlightenment or insight into the questions about irrational numbers, then let me know. Let me know. And I will see you next time.